Now that we have a better idea of what humidity is and the various ways it can be expressed, how do you actually measure it? Technology has given us some wonderful ways to gather data on humidity, and we'll have an example of one of those momentarily. There are, however, some simpler ways to measure humidity, and very cheaply. We're going to take you through one of these methods using a device called a Sling Psychrometer, which is about as low-tech a measurement of humidity as you can get. We're also going to show you how the Sling Psychrometer can help you estimate the various types of humidity using a graphical device called a Psychrometric Chart. Before we go on, just a word about terminology. The prefix psychro is usually used today as a synonym for moisture in the air. We use a psychrometer to measure humidity, or we convert between the various measures of humidity using a psychrometric chart. All these things are derived from a suite of equations known as the psychrometric equations, which don't really describe humidity, but actually describe the energetics of the change of state of liquid water to vapor. The prefix psychro is actually derived from the Greek word meaning cold or frozen, and you'll see that meaning crystal clear just now. As you watch the video to follow, I want you to keep 4 questions in mind. What's the reason for swinging the Sling Psychrometer? What's the point of having a wet bulb thermometer and a dry bulb thermometer? What's the wet bulb thermometer measuring, and how does that compare to the dry bulb thermometer? And can you think of another way the same thing can be accomplished?
I have in my hands a Sling Psychrometer. This is a device that has 2 thermometers in it, and as you can see, one has a sock over the bulb of the thermometer. This end contains a small reservoir of double distilled water. Now, if I take this device and I swing it around until both temperatures of the thermometers come to equilibrium, one will show air temperature because it has no sock on it, it's just being ventilated by the air, and it will actually reach something very close to air temperature. And the other is evaporating water until it comes to its maximum evaporation point, and then it'll stop, the temperature will stop going down. That will be the wet bulb temperature. From those 2 temperatures, when I read this, we'll be able to calculate both relative humidity and absolute humidity. So now I'll stop, look at the temperatures, and I look at the wet bulb first because it'll start going up, and I see that it is at 15.9 degrees. And then look at the dry bulb temperature, and the mercury is at 28 degrees exactly. Now I can take these and put them one opposite the other in this scale, 15.9 opposite 28, and what I'll get from this is in the order of 28% relative humidity. But we'll use a psychrometric table to calculate that more accurately, and we'll also calculate the absolute humidity, which is necessary for further work on animal heat balances. A handy way to calculate relative humidity from the temperatures of the wet and dry bulb thermometers of a Sling Psychrometer is to use a psychrometric chart. There are also various kinds of software tools available for free on the internet that you can use to do this, but using a psychrometric chart gives you a graphical view of the results of your measurements. Thus, it's very useful to know how to use a psychrometric chart. Not to mention the fact that the internet is not always available in the field. Here's what a psychrometric chart looks like. Along the horizontal axis is the temperature of the dry bulb that also represents air temperature. The vertical axes show the vapor density in the air, usually in units of grams per cubic meter, and the dew point temperature. It looks pretty intimidating and complicated, but let's take the graph apart and put it back together piece by piece. Once you understand it, it's very easy to use. So now we'll erase all these curves and build a psychrometric chart piece by piece. The anchor of the psychrometric chart is this curve, which shows 100% relative humidity over a range of dry bulb temperatures. This curve is derived directly from the relationship between temperature and water vapor pressure. Remember that 100% relative humidity corresponds to a condition of the partial pressure of water vapor being equal to the total water vapor pressure. The series of curves that fills in most of the chart are simply percentage values of the 100% humidity curve. Here's the curve for 90%, 80%, 70%, and so on. When we start to get comparatively low relative humidity, there's quite a lot of open space on the graph, so we can begin to fill in intermediate values like 25%, 15%, and so on. And when we get down to relative humidity values in the single digits, we can fill in even finer differences and humidities from 8% to 6% and so forth. That's reasonably easy to understand. Now let's fill in the wet bulb temperatures. Wet bulb temperatures on the psychrometric chart correspond to a series of parallel lines sloping downward across from the 100% humidity line to 0 on the horizontal axis. The wet bulb temperature is calculated from the heat balance for water evaporating from the wet thermometer bulb. The calculation is rather complicated, and we won't trouble ourselves with the details of that here. Suffice it to say that wet bulb temperature is the lowest temperature attainable by evaporation into the ambient air by a properly ventilated psychrometer. Thorough ventilation of the thermometer bulbs is a precondition for correct reading of humidity. The basic point is that the wet bulb temperature is going to be proportional to the absolute humidity of the air. A low humidity will depress the wet bulb temperature at any air temperature because there will be a high evaporation rate, and therefore a lot of cooling. A higher humidity will produce less cooling, and the depression of the wet bulb temperature will be less. At 100% relative humidity, there will be no cooling at all, and the wet bulb temperature will be equal to the dry bulb temperature. There are also other conditions that factor in, such as the altitude. This particular psychrometric chart is for an elevation of 1500 meters, which is pretty close to where we are at Ochiwarongo. Okay, now that that's all filled in, let's take the results from the measurements I just made using the Sling Psychrometer. Remember that the dry bulb temperature in that case was 28 degrees. So we begin by drawing a vertical line at the point on the horizontal axis that equals 28 degrees. Now for the wet bulb temperature. Our wet bulb temperature was 15.9 degrees. Notice that the parallel lines for the wet bulb temperature aren't spaced evenly, so we'll just estimate that the wet bulb temperature is about here. We then draw a line parallel to the other wet bulb temperature curves. The two lines, one for the wet bulb temperature and the other for the dry bulb temperature, intersect at this point here. If we look at our relative humidity curves, we see that the intersection falls just slightly below the curve for 30% relative humidity. You'll remember that the direct reading from the Sling Psychrometer was 28% relative humidity. Pretty good agreement, I would say. That's how you read relative humidity from a psychrometric chart. We can also use the psychrometric chart to tell us something else we didn't know, and that is the dew point temperature. To estimate that, we simply extend a horizontal line from the point of intersection for the wet bulb and dry bulb temperatures to the dew point axis. This horizontal curve intercepts the vertical axis at a point a little above 9 degrees. We'll estimate this as 9.3 degrees. That is our dew point temperature. If we cool the ambient air to that temperature, dew would begin to form. Let's give ourselves a little more practice with this chart. Let's pretend that we had measured a dry bulb temperature of 28 degrees as before, but now the wet bulb temperature reads 25 degrees. Once again, we extend the line for the wet bulb temperature of 25 degrees until it intersects the dry bulb temperature line of 28 degrees. That intersection corresponds to a higher relative humidity. This one a little above 70%. We'll call it 72%. Now, to obtain the quantity of water in a volume of air under these conditions, extend a line from the intersection to the left to the vapor density axis. This gives the water vapor density under these conditions as 21.6 grams of water vapor per cubic meter of air. Finally, extending a line horizontally to the right from the intersection to the dew point axis shows that the dew point is now higher, about 23.8 degrees. If we cooled ambient air of 72% relative humidity to this temperature, dew would form. This illustrates the behavior of the dew point temperature. The higher the relative humidity, the higher the dew point temperature will be. You can download printable versions of the psychrometric curve from various sources, including Wikipedia. If you have a Sling Psychrometer or even a table of wet bulb and dry bulb temperatures, you can calculate relative humidity and dew point.